Okay, in this video, we will look at the symmetrical of the waveform and how we can use that to calculate the Fourier series coefficient, the A0 or A0, AN, and BN. So it is important for you to recognize symmetrical signals, okay, the symmetrical signals of the Fourier series. Basically, there are three types of symmetrical signals. We have even, we have odd, we have half wave symmetry, and actually we even have quarter wave symmetry and hidden symmetry. But the other two are not really important. So it is enough for you to uh, differentiate or to know what is even symmetrical signal, odd symmetrical signals, and half wave symmetrical signals. Now first let's look at the even symmetrical signals. All right, so here we have an example of even symmetrical signals. All right, so basically the function ft, it is called even symmetrical or even symmetry when it is symmetrical at the vertical axis. Okay, so we have a signals here, right? And this is the vertical axis or y-axis. And if we look at this side, the signal, and it is symmetrical to this axis, right? Then it is called even symmetry. Okay, same thing with this, right? If this side here is similar to this side at about the vertical axis or y-axis, then it is called symmetrical signals. All right, so what can we use um, if it is an even symmetrical signals? Then we can simplify. Okay, basically we can simplify the calculation of a naught, simplify the calculation of an and also bn. All right, let's just go back to the previous slides. Okay, this is in the um, previous video which I have explained this. So the Fourier series, basically we want to prepare the Fourier series equation here. This is the Fourier series equation, right? So we have to determine a naught, we have to determine an, and we have to determine bn, right? So an and a naught, an, and bn has its own equation, all right? Has its own equation. So we have to calculate all these three for every function, okay, for every periodic signals. Now since for example that one we have even symmetrical signals, okay, or even symmetrical of periodic function, then we can simplify by not having to calculate the bn. All right, so straight away we can assume bn is 0. So that's how what's the benefit of knowing the signals is either even, odd, or half wave symmetry. No, so since we know that this is even symmetry and even symmetry of periodic function, then we can assume bn is 0. All right, bn is 0, and then we still need to calculate a0 or a0, and for an it is now we can simplify as this, right? So can assume bn is 0. So basically if you look at the uh, vertical axis here or y-axis here, if you can fold, if you can imagine that you can fold this at this axis and it will still have the same waveform, then it is called even symmetry. Okay, next is odd symmetrical signals. All right, so in odd symmetrical signals, we basically right. So there are two steps. If you want to imagine, okay, first is you to fold the signal at this axis. All right. So sorry. All right. So this waveform, if you fold at this axis, then you will get something like this, right? But the second step is to fold at this axis, which is from this, then you will get this, right? So it is now symmetry to the positive cycle here, positive side here. So it is called odd symmetry. All right. So for odd symmetry, you can basically assume A not is 0, AN is 0, so you just have to calculate for BN. Alright, you just have to calculate for BN. And take note here. Take note that AN and BN here is 2 over T, okay, integration from 0 to T of ft cos n omega dot T, alright. Right, same thing for Bn, integration from 0 to T ft sine n omega dot T. So 2 over T here, right? But when you consider that it is an either even or odd symmetry, it is now 4. Okay, that's the slight difference. Okay, that is the slight difference. So 4 over T, instead of 2 over T, it is 4 over T. And instead of T, it is T over 2. All right, so you just need to find AN from 0 to T over 2 here. All right, so the FT here is only consider FT from 0 to T over 2 here. All right, that is even. And the same thing for odd. Instead of 2 over T from the original equation of Bn, now you will use 4 over T. Okay, you will consider 4 over T integration of ft from 0 to T over 2, right? So now ft for this example, all right, so ft is this with this straight line and this straight line, so you don't have to consider this straight line. Okay, and then next is half wave symmetry. Do we have other examples? Okay, let's look at other examples of odd symmetry, right? So here we have discussed this, that this is the waveform. If you fold here, you will get this, and then you will fold here, you will get this, which is now it is an odd symmetry. Same thing for this second signals. If you fold here, then you will get this, right, which is the reverse of this. But if you fold here, then you will get the same. All right, so that proves that this is an odd symmetry signal. Okay, same thing for this. Fold here and then fold here, right? So if you do the first fold, you will get something like this. Yes, and then if you do the second fold, you will get the same thing. So this proves that this is an odd symmetrical signal. So now let's look at half wave symmetry. So in half wave symmetry, a function is half wave symmetric if each half cycle is the mirror image of the next half cycle. All right. So basically, instead of folding the waveform, the half cycle of the waveform, you shift it to the left by half cycle and then fold. And if it shows the same waveform, then that is an half wave symmetry. For example, this one, if you shift, you'll get this, and then you fold, you'll get this. So this proves that it is an half wave symmetry. Let's look at several examples we have here. Right, it's the same thing. Okay, let's look at this one. So this is one full cycle from up to t. So we just look at the half cycle here, right? So shift the half cycle, you will get this, and then you fold it, you will get this. So it proves that this is an half wave symmetry. So for half wave symmetry, you can simply assume a naught is 0. You still have to calculate an and bn, but no need to calculate for even number or even n. Okay, and same thing for over t, integration from 0 to t over 2. All right. So you can see here that this is also not odd symmetry. Okay, if you fold it here, you will get this, something like this, and then if you flip it here, you will get this, which is different. So this is not an odd, so it is an half wave symmetry, right? So it could looks like an odd symmetry as well, but it is not. In this case, let's look at it. If you fold here, you will get this, and then when you fold here, you will get this. So in this case, this is an odd symmetry as well. So this is half wave symmetry as well as odd symmetry. All right. All right. So yep, same. Another example. This is an half wave symmetry and also an odd symmetry. But another example, it is an odd symmetry but not half wave symmetry. So it can be either both or just one symmetry. All right. Next is quarter wave symmetry. All right. So quarter wave basically is both half wave symmetry and even or odd symmetry. Okay. So if the waveform is having both half wave and even or odd, then you can also call it quarter wave symmetry, right? Half wave and even or half wave and odd. So if the waveform are in these two conditions, it is called quarter wave symmetry. So basically, you can basically assume AK is this value. All right, to simplify your calculation of the Fourier series coefficient. No need to calculate for Bn, no need to calculate for A0 and so on. So you immediately can identify that this waveform is half wave and even symmetry. You can immediately just use this to calculate the Fourier series coefficient. All right, same thing for this. So to explain, basically, if you so to explain this, basically even symmetry for a quarter wave. Okay, so we have from 0 to t here, this is the half, this is the quarter. So even symmetry for quarter wave. So basically, if the quarter wave of this is symmetrical at the y-axis, which is even, then it is even quarter wave symmetry. If the the quarter wave here is flip here or fold here, then it's the same, then it is called odd quarter wave symmetry. Let's look at this. Right, this is the waveform for quarter wave. If you fold it here, then you will get this, and if you fold it here, you will get this. So this is odd quarter wave symmetry. And then finally, hidden symmetry. So this is an example of hidden symmetry. Straight away, this is definitely not an symmetrical signals. All right. However, if we do some modification on the waveform, then we can make it symmetrical signals. All right. So for example here, if we shift the waveform vertically, all right, from 0 to a here to half of a negative and plus half of a, right? So basically shift it down, right, to look like this. Example, if this is 2 and this is 0, now this is 1, this is negative 1. So now we can make it symmetrical signals. So basically example here, this is 2, this is 0. Now we shift it negative 1, this is 1, this is negative 1, right? We have shifted down here. Then it is now an odd symmetrical signals. Okay, this is now odd symmetrical signals. But take note that since we shift it by -1, we have to also not forget to add the coefficient as well, right? Do not forget to represent that shift by changing this to -1. Right, that -1 is here, right? Okay, thank you.